All right, let's just get right into it. You've probably spent years drawing molecules flat on a piece of paper, right? Well, I'm going to let you in on a little secret. That's basically a lie. Molecules are actual 3D things, and today we're going to uncover the one simple secret that lets you figure out what any molecule really looks like. And we're going to kick things off with a mystery you might not have even known was a mystery. We all know H2O, water, but have you ever stopped to ask, why is it always drawn with that weird bend in it? Why isn't it just a nice, neat, straight line? That's the question we're going to crack today. So on the left, you've got what makes sense on paper. HOH, a straight line. Easy enough. But in the real world, it looks like the molecule on the right. It's actually bent. And understanding why we get from that wrong guess to the right shape, well, that's the key to everything. Now, this secret has a name. And I'll be honest, it sounds way more complicated than it is. VSEPR Theory. That stands for Valence Shell Electron Pair Repulsion. Yeah, I know, it's a total mouthful, but don't let the name scare you. Because all that VSEPR really means is this. It is just a super fancy way of saying that pairs of electrons, because they're all negatively charged, are always trying to push away from each other. They just want to be as far apart as possible. That's it. That's the whole secret. So, the most important thing to get is this. This entire complicated-sounding theory really just comes down to one simple rule. Electrons need their personal space. You know how you don't want to be squished up against someone on the bus? It's the same deal. Electron pairs are constantly shoving each other away to get some breathing room, and all that shoving is what actually carves out the molecule's final 3D shape. Okay, let's start with the easiest possible case. Imagine you have a central atom, and it's connected to just two other things. And when I say things, I just mean groups of electrons. How would you arrange two things so they have the most personal space they can get? Well, you'd put them on completely opposite sides of each other, right? And that creates a perfectly straight line. We call that shape linear. The angle between them is a perfect 180 degrees. You literally cannot get them any farther apart than that. And check this out, it doesn't matter what kind of bond you have. See, in beryllium dichloride, you have single bonds. In carbon dioxide, you have double bonds. And in hydrogen cyanide, you've got a single and a triple bond. VSEPR theory doesn't care. It sees all of those as just one thing pushing away from the center. So if you've got two groups, it's always going to be a straight line, 180 degrees. Simple. Okay, two things is a piece of cake. So let's level up. What happens if our central atom has three things attached to it? How do they spread out to get the most personal space? They spread out into this really cool symmetrical shape we call trigonal planar. Trigonal because there's three things, and planar because the whole molecule is totally flat. Just think of a peace sign. The angle between each of the bonds is a perfect 120 degrees, so everyone gets the exact same amount of room. Okay, now this is where it gets really fun. Up till now, all our things have been bonds connecting to other atoms. But what happens if one of those things isn't a bond at all? What if it's just a pair of electrons sitting there, what I like to call an invisible bully? This is a lone pair of electrons. It is absolutely a thing, just like a bond is. It's a big blob of negative charge, so it still needs its personal space and it pushes everything else away. But here's the twist. Even though the lone pair totally controls the geometry, when we go to name the final shape of the atoms, we pretend we can't see it. It's there, but it's invisible. Let's see this in action. It makes so much more sense. On the left, we've got boron trifluoride. 3 bonds, no lone pairs, no bullies. It's our nice, flat, 120-degree trigonal planar shape. But now, look at sulfur dioxide on the right. It also has 3 things around the sulfur, 2 bonds and 1 lone pair. That invisible bully shoves the 2 oxygen atoms down and away from it, so the molecule isn't linear, it's bent. And that invisible bully, well, it's actually extra pushy. Because it's not being held tightly between 2 atoms, it spreads out and takes up more space than a regular bond does. And it uses that extra space to shove the other atoms even closer together. That's why the angle in SO2 isn't a clean 120 degrees. It gets squeezed down to something a little less. All right, you ready? Final level for today. This is the big one. The arrangement you're going to see all the time, what happens when we have 4 groups of electrons all pushing each other away. Now, with 4 things, we finally have to break out of a flat 2D world. You might think they'd make a square, at 90 degrees, but they can get even farther apart if they pop out into 3 dimensions. This makes a shape called a tetrahedral. The best way to picture it is like a tripod, but with a fourth leg sticking straight up. And the magic angle here is 109.5 degrees. And this is so cool. This one tetrahedral shape is like the parent of a whole family of other shapes. Start with 4 bonds, like methane, that's your classic tetrahedral. Now, what if we swap one of those bonds for our invisible, pushy lone pair? The atoms that we can still see now form a short little pyramid. We call it trigonal pyramidal. Okay, let's do it again. Swap out another bond for a second lone pair, and what shape are you left with? A bent shape. And remember how I said those lone pairs are extra pushy? This chart shows it perfectly. Methane, with 0 bullies, has that perfect 109.5-degree angle. Ammonia comes along with 1 bully, and it squeezes the bonds down to about 107 degrees. And then there's water, with 2 of those bullies squeezing the bonds even tighter, all the way down to about 105 degrees. And there it is. We figured it out. The reason water is bent is because that central oxygen atom has 4 electron things pushing each other away, 2 bonds to hydrogen atoms, and 2 invisible, extra pushy lone pairs. Those 4 things set up a tetrahedral shape, but once you ignore the lone pairs and only look at the atoms, the shape you're left with is bent. So here's your toolkit. From now on, you can predict the shape of pretty much any molecule. Step 1. Just count up the total number of things on the central atom. That's all the bonds plus all the lone pairs. Step 2. Arrange those things in space so they're as far apart as possible, linear, trigonal planar, or tetrahedral. And step 3, my favorite part, pretend to cover the invisible lone pairs with your thumb and just name the shape of the atoms you can still see. And here it is, the whole shebang in one place. This cheat sheet is your new best friend. It ties everything together, how the total number of groups gives you the base shape, and how swapping bonds for lone pairs changes the final name. Seriously, take a screenshot of this. It's the key to everything. So we started with a really complicated, intimidating name, and we discovered that the whole thing was built on one super simple rule. Electrons need their personal space. It makes you wonder, doesn't it? If one simple idea can unlock the 3D shape of almost any molecule, what other complex ideas out there are just hiding a simple secret, waiting for us to find it?